Question 7 then is in two very clear parts. So we start off with 6 marks for the Prim's algorithm on the table, and then we go into a sort of a nearest neighbour type problem after that. So we've got the company operating their steam railway, and we're starting at P. We're going to find a minimum spanning tree to connect the vertices. So the first thing I'm going to do is I'm just going to draw out my skeleton spanning tree. So this is just all of the vertices together. And I don't know what order they're going to go in, so I might end up with it not being particularly neat. But this way, I'm going to be able to check that which ones I visited, and I think it just helps me work out where I am. So I'm starting at P. So I'm going to when it's asking to state the order, you need to make sure that you're putting the order above here. So I'm starting at P. So I'm going to look down P. What's the fastest? It's going to be P to T. So I circle T. I'm going to visit T second, and I've now visited P, started with P, and I visited T. And then in my graph here, I'm then going to draw the link between P and T. So now I've got the options of either going somewhere from P or from T. So the shortest is going to be T to S. So I'm going to visit S third. Let's draw T to S on my spanning tree there. And I've now been to S, so that one can get crossed out as well. So now I get to look down 3 columns. So I'm looking down this P column, I'm looking down the S column, and I'm looking down the T column. And I'm thinking of where I haven't been yet, what is going to be my fastest route. And I can see that there's a 7 there. So I'm going to go from P to R. So now P to R, draw that in there. R, I'm now visiting 4th, and I'm going to cross out R. So I've now been to R as well. So I need to only go to the 2 vertices I haven't been to yet, which are Q and U. And that's really easy to see if I'm keeping my minimum spanning tree and drawing that as I go. So I'm just trying to get rid of the highlight for my two points that I haven't been to yet. So looking down there then, the next smallest, the next fastest route is going to be R to Q for 8. So R to Q, Q I'm visiting 5th, and I've now been there, so I cross it out. So now I just need to visit U. There are 2 possibilities for this one. I can either go Q to U or I can go T to U. Now, when in the mark scheme, it just says you can use either. So let's go T to U, go to U 6th, cross out there, and connect up T to U. So what I've got here is I've clearly stated the order in which I selected the vertices, because that is this top row here on my matrix. I've shown which vertices that I've selected because they're circled in there, and I've also, along the same time, I've drawn my minimum spanning tree. So that's already done. I don't have to worry about now going back and thinking about, oh, what order did I do it in? How does my minimum spanning tree work? It's all done. And with that, I've now got my first 6 marks for this question. For part B then, we're moving on. So this is down here below. We're now looking at a similar situation, but with a new station, so with V being opened. And what we're going to be asked to do is to be finding some tours to actually visit all of these stations. So the other station is open, the minimum cost for travelling is on there, and we have all of those copies of the table which you can do your workings on. I'm just going to do all the workings here and then potentially rub out and come back if I need to. So Arjun is on holiday. He plans to visit each station. He intends to board at V, visit all the stations only once before returning to V. Okay, so this is not now a minimum spanning tree. This is clearly a travelling salesman problem of having to visit each one. So by first removing V, obtain a lower bound for the minimum travelling cost of Arjun's tour. You may use figure 1 for your workings. Now, without V, it's actually what we've just done up here, because this is the same thing but without V. So what the lower bound algorithm says is to remove one of the vertices and find the minimum spanning tree. So using what we've already done in part A, so B part 1, from A, the minimum spanning tree is equal to 36. And then what do we have to do? So we've got our minimum spanning tree and we add in V by its two shortest edges. So in this case, we're going to be adding in V by a 12 and a 14. So we're then going to add in 26 more. So let's say we're going to be using V to S and V to U. So that gives me my lower bound of 62. And that is worth 3 marks. Okay, so identifying that the minimum spanning tree, and obviously if you did it again, that's absolutely fine, but this is the faster way of doing it. And then we are adding in 26, which comes from VS and VU. So this is a lower bound, so that equals a lower bound for the TOR, for the minimum TOR. Okay, so then we're into part 2, and I'm going to remove that, but leave this one here. Use the nearest neighbour algorithm twice, each time starting from V, to find 2 different upper bounds for the minimum cost of Argent's TOR. State with a reason which of the 2 answers gives you a better upper bound. So the lower bound algorithm, remember, we're told where to start from, so we're going to start from V. So it doesn't matter because this is symmetrical, so it doesn't matter which way we're going to do this. So if I'm starting from V, and now the way in which I always do this is I do draw out the skeleton again. And the reason I'm drawing out the skeleton is just so that I can make sure that I visited every place I want to and return without making any errors. And I just think it does really help me focus what I'm doing. So I'm starting at V. Where shall I go? Well, let's go to U because that's clearly the quickest. So V to U. I'll just do my workings over here so I can go over if I need to. V to U for length 12. I'm now at V. Now I don't want to go back, sorry, I'm now at U. I don't want to go back to V, but I can go to any of the others. So I can go to one of the 2 10s. And this is clearly where I'm going to have my choice. So let's do one way first. So let's go to T. So I can go to T for length 10. But equally, I could have gone V to U, and then I could have gone to Q, also length 10. So I just want to make sure that that's there. I'm now going to worry about this first one, and then we'll carry on. So I've just gone U to T. So I'm now at T. Where shall I go next? Let's go to S. So I go to S for length 5. Cross out S. I've done T as well, haven't I? So I'm now at S. Where shall I go? I can go to R, Q, or P. So I'm going to go to Q. So S to Q, which is the length 10. Now I'm at Q. So I can go to R or to P from Q. So Q to R or P, I'm going to go to R for length 8. Let's just bring that over. For length 8, I'm going to R. And then finally, I'm going to need to go R to P. So R to P is length 7. And then remember that he wanted to return to V. So I've got to go P to V for 15. Okay, so whilst it's not necessarily as neat and or as straight line as I'd like it to be, that gives us one possible TOR here. So V, U, T, S, Q, R, P and V. And if we add those up, it comes to 67. The alternative was obviously where I chose to go to T instead of Q. So if I've been to V, I've been to U, and I'm now at Q. So let's remove this because it's just workings. All this is just workings. The only thing that I'm wanting to be marked is what is in this box here. This is my actual, what I want my examiner to look at. So I've gone U to V and V to Q. So I'm now at Q. I want to go anywhere I haven't been yet. So I'm going to go to R for 8. Because Q to R8 is the shortest route from there. So to R for 8. So I've now been to Q as well. I'm now at R. So I'm going to go R to P for 7. Now I've been to P. I've been to R. And I'm at P. So I can go to S or I can go to T. So let's go to T for 6. So P to T is 6. And then finally I'm at T and I want to go to S. So that's going to cost me 5. And then once again, like in the first one, I need to return to V. So S to V. So S to V, if I'm at S and I'm going to V, that's going to cost me 14 more. So I've got 14 there. And now if I add up these ones, it comes to 62. So I've got 2 possible upper bounds here. And then it says, the question says, state with a reason which of the 2 answers gives the better upper bound. So I'm going to write beneath it, 62 is the best upper bound, or the better upper bound, should I say, since 62 is smaller than 67, and for the upper bound we want the smallest possible upper bound. And then we've got, hence find an optimal tour of the 7 stations. Explain how you know that it's optimal. So what we've actually been able to show here, I'll just show you this in green, just highlight where we've been here, is that the upper bound and the lower bound are the same. So there's an upper bound or a lower bound that's the same. So what we're going to say for part 3 is that if we have our inequality, which is the lower bound less than or equal to the optimal tour, less than or equal to the upper bound, and then substitute 62 for both of these, we can say that 62 is the optimal tour. Is the optimal tour since the upper bound and lower bound are equal, or since the lower bound gives a tour. So it's either since the lower bound gives the tour, or since the lower bound has the same value as the upper bound. Since the lower bound has the same value now, as well as this, we're actually asked to find that tour. So you're going to want to write it out one more time. All of this, lovely as it is only worth 1 mark. You have to write out what the tour was. So the tour was the one that gave us the 62, so it's this one here. So you're just needing to write out all of those letters in order. V, U, Q, R, P, T, S, and back to V again. And you needed to write out both of those to get the final mark.